Okay, hi team. On to synchrotron. Now, this is going to be a quick one. It's the last one in the idea of particle accelerators. And here, it's all about this word synchronized. So it's synchrotron. Presumably we already had cyclotron. So it's an advance on the cyclotron. And the key point is, if you've seen people synchronize swimming, not necessarily the school team of synchronized swimmers, but if you've seen people synchronized swimming, they should be swimming all precisely synchronized. And what does that really mean? That means that they're doing things in time. They're doing the same things at the same time. So if you're going to synchronize something, you're going to get the timing right. And that's the interesting aspect of the synchrotron. Now, you've got to remember, we've got to go back to some aspects of the last video and say, okay, if we've got a linear accelerator, we know we're just doing one acceleration, the timing's not an issue. When we come to doing things like a linear accelerator like this, we can fire something along, and if we get the voltages right on the cylinders, it will just fly along and we just do one test. So we just do one test it right, we just have to get the charge on the cylinders organized. And in a cyclotron, when you made a cyclotron, you had a constant voltage change between the two Ds. So now, here we've got something completely different. When I say constant voltage change, the frequency of the changing alternating supply to the Ds that provides that electric field was fixed. Now, this is completely different. Now, in a synchrotron, we've only got one path. So this is just a general schematic of the idea. It's not super correct. We've got one path, and if I have my particle, I'm not going to deal with the details of how you inject the particle and how you may have it. There's loads more complicated bits, and I'm going super simple. I inject a particle at speed, it goes around the circle, and at one point in the circle isn't a circle. They don't kind of show you this in the basic videos. You have a straight line section which has an electric field. And my electric field is so you have a straight line section of the ring which will have an electric field which presumably will attract my proton, and then as my proton comes in, it will then swap over so that and give it a kick to make it go faster. So it's going to accelerate through the field, gain kinetic energy, go around the next bit of the circle faster. And it'll go around, so the second time around it's a bit faster, and then it gets another acceleration from my quickly alternating electric field, which attracts it and then repels it. So it has to change, so it has to be negative on this side as it approaches, and then swap over and become positive. Once it's in there, we need positive over here and negative over here to accelerate it across. And then it's going to go even faster the next time. Now clearly, if it's going to go in a circular path through these magnets, first of all, it should only be a curved path through the magnet, then it should be a straight line. Curved path, straight line, curved path, straight line. I regret now that I didn't use my ruler. So only the magnet should be curving its path. When it's not in the magnet, it's a straight line. As it goes faster and faster, to keep it in a circular path, the magnets will have to increase their magnetic field strength. So we're going to have to somehow organize or synchronize an increase in magnetic field strength, and we're going to have to be ready to switch this alternating electric field on faster. So it comes on, it's ready now, next time it's now, next time it's now, and this is going to have to come on more and more frequently, so the frequency will change here because our particle is doing exactly the same circle all the time. As it goes faster, it gets here more often. So there are some very important differences between the synchrotron and the other types of particle accelerators we've looked at. But I think the Lego model of the synchrotron is very good, and we'll look at that video together. I've posted that video in the playlist higher in the normal video playlists. So if you look playlists higher, you should get the video that is the synchrotron Lego, which is quite good. And that really is all I wanted to suggest, other than these things generally go around in a beam between the magnets, And these magnets are generally a magnet above and a magnet below the beam pipe. So you would have your beam pipe, a magnet above and a magnet below, and a magnetic field would be vertical. So the beam experiences a force to the center of the circle. So your magnetic field is straight down, your particle's going that way, and you have it organized so that it goes, the force is towards the center of the circle. So that, there we go. So it's bottom of the magnet, beam pipe, top of the magnet, like that, and the magnetic field going down the way, giving us a force towards the center of the circle. So, the only other key aspect of the synchrotron is we haven't dwelt on how you get the particles in or out, or the nature of how you get them to collide. And that's partly because it becomes increasingly complicated. At CERN, they take protons one way around, and they take antiprotons the other way around. So they have, because they're opposite charges, so they actually have different, they have one particle going one way around and another particle going the other way around, and they keep them separate. And when they're happy they're all at an appropriate speed, they change it so that they collide inside an enormous machine that's designed to observe that collision. So they have a proton and an antiproton. I don't know why I've represented them with very different size objects. It's not very helpful. So that's how they do it at CERN. But loads more details. If you wanted to take an interest in this, obviously there's loads more details. But that's the basics. Now, going back to compare these three different types, there are some interesting things to consider looking at the three different types of accelerators. And I don't want you to get ahead. So I'm going to look at the three different types and say, if you understand them, you'll know about the magnetic fields and the electric fields in each one. So just to sum, our linear accelerators, our cyclotrons, and our synchrotrons. Okay, first of all, in a linear accelerator, quite simply, there is no magnetic field because it goes in a straight line. The magnetic field is only ever required to keep the particle moving in a circle or to keep it on a curved path. So there's no need for that in a straight line, and we just have an alternating field between the cylinders, and that's what happens. In a cyclotron, we have that fixed magnetic field pushing down from the top of the cyclotron. I think at the end of the cyclotron, when I tried to kind of put the whole thing in context and said, your cyclotron's going to be between two massive coils, and the coils are going to be in water baths essentially, because you needed enormous magnetic fields. And these are my magnetic field lines, if you remember. So in a cyclotron, the magnetic field is fixed, and it's just running down through the apparatus while you're doing your while your proton's doing its spiral path in there. So, and in a cyclotron, the alternating field between the positively charged, negatively charged, positively charged, negatively charged, positive, that alternating field thing goes at a fixed rate. You don't change the switching rate. It's a fixed rate. Now, so the electric field is alternating and the magnetic field is fixed. Now, in a synchrotron, we're going to have a situation where we've got an alternating electric field at that one point where in the ring where we accelerate the particle, and then we're going to have a magnetic field that is increasing with particle speed, because that's different to the other. Sorry, so that's significantly different to the other ones, is it? This needs to be synchronized with that and with the particles, and that's why it's a synchrotron. There's a lot more things to organize. Right, what I would like you to do is to look at the questions that I have put on the website, and they are in our classroom, and they are in a new tab of where the assignments appear. Up here on the left, I put a new tab which is particles and waves. Particles and waves. If you click on that, you'll find I've got some course questions, and I'd like you to do the very long question which is on page 13, and there's stuff to help you on page 14. So I'd like you to sort out the missing words on page 13 and 14. That's not particularly easy and it's quite a long task. So if you take your time with that, and I'll catch up with you and give you some feedback. Okay, be good.